Dominant mode in a rectangular waveguide is TE10 because this mode has option A, no attenuation, option B, no cutoff, option C, no magnetic field component, option D, highest cutoff wavelength. So the solution to this question is, it's a straightforward question. So dominant mode in a rectangular waveguide is TE10. So what is the definition of dominant mode? A dominant mode means a dominant mode is a mode which has lowest cutoff frequency or highest cutoff wavelength. Highest cutoff wavelength. This is the definition of dominant mode. So straightforwardly the answer is D, because it has highest cutoff wavelength. Next problem is a rectangular hollow metal waveguide has dimensions A is equal to 2.29 centimeters and B is equal to 1.02 centimeters. Microwave power at 10 gigahertz is transmitted through the waveguide. Through the waveguide in the TE10 mode. Calculate cutoff wavelength and guide wavelength for this mode. So I am giving a hint to solve this question. Here A is given, B is given, and A is equal to 2.29 centimeters, B is equal to 1.02 centimeters. Microwave power at 10 gigahertz is transmitted through the waveguide. So F is equal to 10 gigahertz. Then they are asking what is the cutoff wavelength. So first of all calculate cutoff frequency. Fc is equal to C by 2 into square root of m by a whole square plus n by b whole square. Here it is given TE10 mode. So Fc is equal to C by 2a. So implies lambda c is equal to 1 by Fc. So directly you can calculate cutoff wavelength. Next they are asking what is guide wavelength for this mode. So we know that 1 by lambda g square is equal to 1 by lambda naught square minus 1 by lambda c square. So here they are asking lambda g. Lambda g is equal to how much? So we know, we calculated just now lambda c. Lambda c we can calculate by using this formula. And the unknown thing is lambda naught. What is lambda naught? Lambda naught is wavelength in free space. So here frequency is given. What is the relation? Generally lambda is equal to c by f. So lambda naught is equal to c by f, where c is 3 into 10 power 8 meter per second by f is 10 gigahertz. So 10 gigahertz means 10 into 10 power 9. 10 into 10 power 9. So this is nothing but 3 into 10 power minus 2, 0.03 meters. Lambda naught is equal to 0.03 meters. So lambda naught known, lambda c known. So directly you can calculate guide wavelength. So if you calculate guide wavelength, you will get approximately 6.03 centimeters. 6.03 centimeters. So calculate and verify your answer. Problem number 7. The interior of a 20 by 3 centimeter cross 20 by 4 centimeter rectangular waveguide is completely filled with a dielectric of epsilon r is equal to 4. Waves of free space wavelength wavelengths shorter than dash can be propagated in the TE11 mode. TE11 mode. So indirectly, the solution to this is indirectly they are asking what is lambda c. What is lambda c? So first of all, calculate cutoff frequency. C by 2 into square root of m by a whole square plus m by b whole square. Here c is equal to 3 into 10 power 8. But here it is filled with the dielectric of epsilon r 4. So I am considering this is c by square root of epsilon r. Square root of epsilon r into 2 square root of m is equal to 1, n is equal to 1. So 1 by a whole square plus 1 by b whole square. A is equal to 20 by 3. So 3 by 20 whole square plus 4 by 20 whole square. So this is equal to c by 4, because epsilon r is equal to 4. Square root of 4 is 2. So therefore 2 into 2 is equal to 4. C by 4 into square root of 9 plus 16 by 20 square. That is equal to c by 4 into 5 by 20, because 9 plus 16 is 25. Square root of 25 is 5 by 20. So this is equal to c by 16. C by 16. So this is equal to 3 into 10 power 8 by 16 meters per second, or 3 into 10 power 10 centimeters per second. So by 16. This is cutoff frequency. This is cutoff frequency. But here they are asking waves of free space wavelength shorter than dash can be propagated. So lambda c is equal to c by fc. This is free space wavelength. So don't consider here c by square root of epsilon r, because they are asking with respect to free space wavelength. So lambda is equal to c by fc. So this is equal to 3 into 10 power or 10 centimeters per second by 3 into 10 power 10 by 16. Cancels out. So this is nothing but 16. Nothing but 16. So 16 or centimeters, because here we consider because here A and B are in centimeters. A and B are in centimeters. So directly we consider all in centimeters. That's why the answer is also in centimeters. So 16 centimeters. Therefore, waves of free space wavelength shorter than 16 centimeters can be propagated in the TE11 mode. So this kind of problem is very important. Next problem is an air-filled rectangular waveguide has inner dimensions of 3 centimeters cross 2 centimeters. The wave impedance of the TE20 mode of propagation in the waveguide at a frequency of 30 gigahertz is the bracket free space impedance eta naught is equal to 377 ohms. Options for this question is 308 ohms, option A, option B 355 ohm, option C 400 ohm, option D 461 ohm. So this is another kind of problem. Solution to this problem is, here it is given air-filled rectangular waveguide of inner dimensions 3 by 2. So A is equal to 3 centimeters, B is equal to 2 centimeters. They are asking what is the wave impedance for a TE20 mode. TE20 mode. So we know that eta TE is equal to eta dash by square root of 1 minus FC by F whole square. So where eta dash is? This is free space. Because here the waveguide is filled with air. Suppose the waveguide is filled with some dielectric constant, then we have to consider epsilon r also into account. That is divided by square root of epsilon r. So this is free space impedance, which is we already know, given 377 ohms. And one more thing we have to calculate is FC, that is cutoff frequency. So cutoff frequency formula we know, C by 2 into square root of m by a whole square plus n by b whole square. Since it is a 2-0 mode, n is equal to 0. So m is equal to 2. That is equal to C by 2 into m by a. That is equal to C by 2 into m is equal to 2 by a. Now implies C by a. equal to C by A. So therefore cutoff frequency is equal to 3 into 10 power 10 centimeters per second by 3 centimeters. 3 cancels. So this is nothing but 10 gigahertz. Nothing but 10 gigahertz FC. F we have to calculate. F is equal to given at a frequency of 30 gigahertz. So directly it is given 30 gigahertz. So what is they directly substitute all the values. So eta T is equal to eta dash 377 by square root of 1 minus FC by F. FC is 10 by 30. 10 by 30 means 1 by 3 whole square, 1 by 9. So this is equal to 377 into square root of 9 by square root of 8. Square root of 9 by square root of 8. So if you simplify this, you will get approximately 399.86 ohms. 399.86 ohms. So if you compare your answers, this is approximately equal to 400 ohms. Approximately equal to 400 ohms. So option C is correct. So the only thing here is you have to keep in mind the formulas. Otherwise it is impossible to solve a waveguide problem. So cutoff frequency, impedance, guide wavelength. So you will get problems based on these formulas only. Next problem is problem number 9. A rectangular hollow metal waveguide of internal cross section of 7.366 centimeters cross 3.556 centimeters carries a 3 gigahertz signal in the TE10 mode. Calculate the maximum power handling capability of the waveguide assuming the maximum permissible electric field inside the waveguide to be 30 kilovolt per centimeters. So this is another kind of problem which is very interesting. Here I am giving a hint how to solve this problem. So here it is given a rectangular hollow metallic waveguide of internal cross section of some dimension. So here A is equal to given 7.366 centimeters, B is given 3.556 centimeters. Carries a 3 gigahertz signal. So the signal frequency is 3 gigahertz in the TE10 mode. So the mode is TE10. Calculate the maximum power handling capability. Maximum power handling capability assuming the maximum power electric field. So E maximum is given 30 kilovolts per centimeters. So then they are asking what is the maximum power handling capability. So This is somewhat related to wave equations also. The problem is a combination of waveguide as well as wave equations. So we know that power maximum or average power capability is half into E square by eta. Half into E square by eta. Since it is a only waveguide of cross section, a particular dimension, which is A. This is A, this is B, this is B. So the maximum power is only limited to this area. The maximum power is only limited to this area. So into AB. Into AB. So half into E square by eta AB. So where E is given 30 kilovolts per meter. So A no we know, B you know, no eta. Eta is what? Wave impedance. So we have to calculate wave impedance here. So eta TE is equal to eta dash by square root of 1 minus Fc by F whole square. Fc is equal to C by 2 square root of M by A whole square plus N by B whole square. So here it is given TE10 mode. So this is nothing but C by 2A. C by 2A. So Fc we can calculate easily. F already given. So eta dash is nothing but eta dash is equal to 377 ohms. Free space. Free space. So calculate eta TE and substitute this eta TE value here. This is eta TE. Since it is given a TE propagation. So half into E square by eta TE AB. So if you calculate, you will get the answer. What is the maximum power capability? So this kind of problem is very interesting problem. So the formula is this one. Since here we are multiplying with AB, why we are multiplying with AB is since the waveguide cross section. So the power is limited to a particular area. What is that area? A into B. So that's why we are multiplying with the maximum power handling capability of the waveguide. They are asking what is the maximum power handling capability of the waveguide. That's why we are multiplying with the AB. So eta TE. So eta TE we can calculate by using these formulas. So directly we can calculate the answer very easily.